In this video, we will learn how to solve for constraint optimization using Lagrangian method. The question is, we have to maximize a utility function of a consumer that he derives from the consumption of two goods x and y, which is equal to 1 upon 4 x raised power 1 upon 3 times y raised power 3 upon 2, subject to the constraint that is 5x plus 2y is equal to 150. 5 is the price of good x, 2 is the price of good y, and 150 is the income of the consumer. Okay, so how do we use the Lagrangian multiplier method here? Let us understand. Okay, so first thing is we write the given utility function, that is u is equal to 1 upon 4 x raised power 1 upon 3 times y raised power 3 upon 2. Okay, given this utility function, we also call this the objective function. First step is we rewrite this constraint. Okay, we set the given constraint equal to 0. That means we write 150 minus 5x minus 2y. We set it equal to 0. This is the first step in solving this question using Lagrangian method. That is, we set the given constraint equal to 0. Second step is to multiply this constraint by lambda on both sides. Okay, and third step is to form the Lagrangian function. Let's denote it by L. So Lagrangian function is formed by adding the given utility function with the resulting budget constraint that we formed. Okay, so utility function is 1 upon 4 x raised power 1 upon 3 times y raised power 3 upon 2. We add to this utility function the resulting constraint, that is lambda times 150 minus 5x minus 2y. This is our Lagrange's function, Lagrange's function, whatever you say. Now third step is to partially differentiate this Lagrange's function with respect to x, y and lambda and set them equal to 0 simultaneously. Okay, so we partially differentiate the given Lagrange's, or rather the new constructed Lagrange's function with respect to x, y and lambda and set them equal to 0 simultaneously to find out the optimal bundle of good x and y. So let's denote by L subscript x denotes the partial derivative of this Lagrange's function with respect to x. So doing the calculation here, so the exponent of x is 1 upon 3, it will become the coefficient. So we have 1 upon 4 to this, we multiply 1 upon 3 the exponent of x. Then we have x raised power 1 upon 3 minus 1. Exponent is subtracted by 1. If we have x raised power n, its derivative is simply n times x raised power n minus 1. That is to say, if we have x raised power 5, its derivative is 5 x raised power 5 minus 1. Okay, so simply uh, we multiply the exponent with x and subtract the exponent by 1. And same logic we have used here. We have x raised power 1 upon 3. Its derivative is 1 upon 3 will become coefficient, or it will be multiplied with x, and 1 upon 3 will be subtracted by 1. So it will become 1 upon 3 x raised power 1 minus 3 is minus 2 upon 3. Okay, so here it is minus 2 upon 3. Other terms will remain you know rather other variables will remain same because we are taking the partials here. So y is power 3 upon 2 will remain same. Okay, now here you can see we have x in this middle term, so derivative of x will be 1, so we will be left with minus 5 and this lambda, and we set it equal to 0. Similarly, L subscript y denotes the partial derivative of this Lagrange's function, and let's take here. So this time the exponent of y raised power 3 upon 2 will become coefficient. So we will have 3 upon 2, then we have 1 upon 4 x raised power 1 upon 3 will remain same because we are taking partials with respect to y. So y raised power, the exponent of y raised power 3 upon 2, it will be subtracted by 1. So it will become 3 minus 2, which is 1 upon 2. 1 upon 2. Okay. Similarly here, derivative of y will be 1. So we will be left with minus 2 lambda, and we set it equal to 0. Then we take the partials with respect to lambda. Since no lambda is involved in the first term, its derivative is 0. Derivative of lambda is 1, so we are left with 150 minus 5x minus 2y, and we also set it equal to 0. Okay. In this equation, when we set it equal to 0, we can rewrite it in this fashion. So it becomes 1 upon 12 here. We have x raised power minus 2 upon 3, y raised power 3 upon 2. If I transpose this minus 5 lambda to RHS, it will become plus 5 lambda. Okay. And similarly in this equation, so it becomes 3 upon 8. Then we have, okay, this is 3 upon 8, x raised power 1 upon 3, y raised power 1 upon 2, and transposing this to RHS, it will become twice lambda, that's positive. Let us say this is equation first, this is equation second, dividing equation first by equation second, and let's do it here to save the space. Okay, so here you can see I can write 1 upon 12, transposing this it will become 8 upon 3 into, here we can do one thing. If I transpose this 1 upon rather this y raised power 1 upon 2 to numerator, its sign will change and it will get multiplied with this y raised power 3 upon 2. And let me show it here. We have y raised power 3 upon 2 in the numerator. If I transpose this, it will get multiplied, but its exponent will change. So it is plus 1 upon 2, it will become minus 1 upon 2. Okay. So bases are same, we can add up the exponent. So we have y raised power 3 upon 2 minus 1 upon 2, which becomes y raised power 3 that's 2 upon 2, which gives us y. Okay, solving these two, we will get only y in the numerator. And similarly, if I transpose this x raised power minus 2 upon 3 to denominator, and we have here, and let me write it here, x raised power minus 2 upon 3 divided by x raised power 1 upon 3. If I transpose this to denominator, it will become 1 divided by x raised power 1 upon 3. Exponent sign will change, it will become x raised power plus 2 upon 3. Again we have same basis, we can add up the exponents and it will add up to 1 upon 3 plus 2 upon 3 is 1, so we will get x in the denominator. Okay, so let us see what we got here when we solved this. So we got y in the numerator and x in the denominator as I have explained. Here lambda and lambda will get cancelled, we will be left with 5 upon 2. Here it becomes 8 upon, or let us try to solve this out here. So we have 4 2s are 4 3s are, so we will get here, which implies 2 upon 3 into 3 is 9, y upon x is equal to 5 upon 2. Solving for y, that gives us y will be equal to 5 upon 2. Transposing this, it will become 9 upon 2, and transposing this, it will get multiplied. That gives us y will be equal to, and let's write it here, y will be equal to 45 upon 4x. Okay, now let's plug the value of y is equal to this stuff into equation third. Let us say this is equation third. So we have 150 minus 5x minus twice, in place of y we have 45 divided by 4x, and it is equal to 0. So we have 150 minus 5x minus, so 2 ones are 2 twos are, we will get 45 divided by 2x is equal to 0. Solving again, we will get 45x. Rather, let's first write this transposing these terms here. So we will get 5x plus 45x divided by 2 is equal to 150. Solving this, so 2 5s are 10, so 10 plus 45 is, I guess it's 55. 55x upon 2 is equal to 150, which implies x will be equal to 150. Transposing 55 upon 2, it will get multiplied but reciprocated, 55. So here we have 5 11s are 5 3s are, so this becomes 30 into 2, which is 60. So the optimal value of x will be equal to 60. 30 into 2 is 60 upon 11. Okay, so this is the optimal value of good x that the consumer will buy. To find out the optimal value of y, simply plug x is equal to this stuff into this function. Okay, so we will have y is equal to 45 upon 4. In place of x we have 60 upon 11. Solving this, we will get y will be equal to 675. 4 ones are 4 15s are, so this will come out to be 675 upon 11. Okay, so this is how we solve this kind of question using lagrangian method. Okay, so optimal bundle that the consumer will consume is 60 upon 11 and 675 upon 11. I hope I make myself clear in this video. Thank you.